Good morning. This is Physics 1020-1090. This is a lecture for Wednesday, March 18th. We're talking about Chapter 24, Wave Optics. This is the first video from the Wednesday lecture. It's about interferometers. Now, interferometers are actually discussed in your textbook in Chapter 25, specifically 25.7 Michelson interferometers. However, I think they fit better in the chapter on interference, so we're going to discuss them a little bit early. We're going to discuss them right now. Okay, so how does the interferometer work? Well, you start with a laser. We're going to take a laser, which is a source of monochromatic, coherent light. That's going to be the heart of the interferometer. It's going to shine out, and the first thing it's going to hit is what's known as a beam splitter. That is sort of a half-silvered mirror, which is going to allow half the light to pass right through it, and the other half is going to get reflected from it. So we're going to separate now the light into two beams, and let's see what happens. First, let's find out what happens to the light that passes right through and goes through the beam splitter. Okay, well, that light comes through the beam splitter and it's going to go hit a mirror. And the mirror is going to bounce that light right back towards the beam splitter. And it'll pass, and at least half of it is going to get reflected from the beam splitter and come down here and get recorded by a light detector down at the bottom. So half the light goes through, hits the mirror, it comes back, and gets detected by the detector. What about the light that got reflected off of this beam splitter, coming from the laser and got reflected? What happens to that light? That light's going to come up, it's going to hit this mirror and bounce back, and then pass through the beam splitter and come down to the detector. Now, you see what you have is you now have two beams of light coming down and hitting the detector. And then the secret is that those two beams can undergo constructive or destructive interference. Just like in Young's experiment where we had two light rays which were separate and then came together to cause interference, we now have two beams that went through two different paths, come together and either give you a bright spot, constructive interference, or a dark spot, destructive interference. Now, the secret to this is that this mirror up here is adjustable. You can move its position up and down. And as you move its position, you're changing the path length of this beam. As you change the path length, you're changing the total distance that the light travels. You aren't changing the distance from this beam because this mirror is stationary. So what you're doing is you're changing whether the light, the two rays, when they hit the detector, are in constructive or destructive interference. If this path changes, if this path is, say, one wavelength longer than this path over here, you'll have constructive interference because they'll be in phase and you'll get constructive interference. But if this path is a half of a wavelength longer than this path, you'll end up with destructive interference because the two rays, when they hit the detector, will be out of phase and you get a dark spot. So as we move the mirror up and down, we have a very nice way to measure distance. So the secret to an interferometer is you have an exquisite way to measure distance by looking at interference between the two light rays. So that's what we're going to use the interferometer for. I want to show you two examples of when you use interferometers. One from astronomy and one from medicine. So let's first look from astronomy. Some of you may have heard of LIGO. LIGO is the acronym. It means Laser Interferometer Gravitational Wave Observatory. LIGO is what discovered gravitational waves a few years ago. It's the device used by the researchers to discover gravitational waves. So it's been in the news a lot. At the heart of LIGO is an interferometer, laser, beam splitter, two mirrors, and a detector to detect the interference phenomena. Now, what happens is when a gravitational wave comes by, it can cause this mirror to move. Gravitational waves, just like electromagnetic waves, are polarized, and we're going to talk about that in the next lecture, which means it might make this mirror move while not making this mirror move because the light is polarized, the gravitational wave is polarized in this direction. So what happens now is if you see this mirror moving back and forth, that's a signal that a gravitational wave has come by. Now, what are gravitational waves? Well, Einstein found that he could extend Newton's law of gravity to give a whole relativistic theory of gravitational waves. Unfortunately, we're going to skip that chapter on relativity. But the point is, gravity doesn't happen at an instance. In Newton's theory, the gravitational force is action at a distance. If you had a change in some masses, there instantaneously you feel a change in the gravitational force. But in Einstein's theory, gravitational effects travel with the speed of light, just like electromagnetic radiation does. So we're looking at these waves of gravitation that propagate out and pass by the Earth. What would be a source of a gravitational waves? It might be, say, two black holes colliding, which is a huge gravitational effect, which sends these waves out through the universe. Now, you have to have very high sensitivity. In fact, you have to have some of the highest sensitivity in all of science. The amount of motion of this mirror, if a gravitational wave comes by, is something smaller than the size of a single atom. So you have to be very sensitive. And in order to make this sensitive, you need to make the two arms of the gravitational detector very long. So the gravitational effect can operate over a very large distance. So these two arms in the LIGO are each 4 kilometers long. 4 kilometers, that's 2.5 miles. They're underground in a vacuum tube, 2.5 miles long, and there's 2 of them, one going in one direction and one in the other. The laser shines, the signals go out, bounce back, and get connected at the detector. Now, there's a lot of sources of noise in this signal. For instance, real small earthquakes that you might not even ever notice would be huge compared to the size of the gravitational waves. Even if a truck drove by or somebody was walking around near the beam lines, you could possibly see noise on a device this sensitive. So the people at LIGO have spent a huge amount of time trying to remove all the sources of noise. But even still, what you really want to be sure you have a gravitational wave signal is you want to build 2 of these. So there's one built in Hanford, Washington, up in the Pacific Northwest. And there's one built in Livingston, Louisiana, in the South. Now, if those 2 far distantly placed interferometers measure the exact same signal at the same time, you can be pretty sure that that signal came from some distant source in outer space and reached the Earth at this, rather than being some local phenomena like a truck driving by. So, what did people see? Well, on September 14th, 2015 was the first detection of gravitational waves. What you had is the LIGO saw a signal, and it looked like this as a function of time. You saw, at first you didn't see much, then you begin to see some wobbles as a function of time, and the wobbles got bigger, and they also got higher frequency, until finally they just abruptly stop, and then you have no signal again. It's called a chirp, and the first signal was from a chirp that was detected both in Hanford and in Livingston, and it's thought that this is 2 black holes colliding gave this signal. They've since seen many gravitational waves. Sometimes they're 2 neutron stars colliding, sometimes a neutron star getting sucked up by a black hole. All kinds of interesting astronomy. It's a whole new way to do astronomy. So the heart of this is a laser interferometer. And if you're interested in LIGO, I'm going to send you some physics girl videos where she visits the actual observatory and can show you around. Fascinating stuff. Now, I know a lot of you are pre-med students, so I wanted to show you a biological application of interferometers. This is called optical coherence tomography. So at the heart is your interferometer, your laser, your detector, your beam splitter. This beam here goes up and hits a mirror, and this is your adjustable mirror that you can move up and down, adjusting the path length of this ray. The mirror over here is replaced by your eyeball. So the light comes into the eye, and what happens is it reflects, but it reflects off your retina and then comes back, and now you're combining two signals, one from the adjustable mirror and one from the retina. The secret about optical coherence tomography is you use light with a very short coherence length. Now let's remember what coherence means. Two beams will only interfere if you have almost exactly the same path difference. If their path difference is different by an amount of the coherence length, the interference will the phase shifts will cancel out and you won't get interference. So we're going to have optical coherence tomography depends on a very, very short coherence length. That way, you won't get any sort of interference fringes unless these two distances are almost identical. So as you adjust this mirror, you really adjust at what reflections you're looking at in the retina. You'll get reflections off of various layers throughout the retina, and the only ones you'll get interference effects from are the ones that come from exactly a certain depth in the retina corresponding to the position of this mirror. So you get these wonderful pictures of the retina and what's happening within the depth of the retina using optical coherence tomography. Let me show you one of those pictures. Here are the pictures from a retina. Over here is a normal retina. This is where the optic nerve comes in, and it's the center of the retina. And you can see the different layers picked up as you scanned that mirror and you looked at the interference fringes. Over here, you have a retina that has this big blurb right there, the black area. That's where the retina is beginning to tear a little bit off the back of the eyeball. So you can see you can use this to diagnose different diseases. Another use of interferometry. By the way, if you're interested in this book, where I got these pictures from, it is Intermediate Physics for Medicine and Biology. Note, I'm one of the authors. If you're interested, you can purchase this book at Amazon.com. Just search for Intermediate Physics for Medicine and Biology. Or if you want to save some money, you can download PDFs through the Oakland Library and read the book online for free. So, it's also the book that's used in our biological physics and medical physics classes. So if you're interested in both medicine and in physics, and you want to take biological physics or medical physics, you can take a look at the book that will be used in the future. Okay, so now that's it for today's lecture. What I want to talk about in the next lecture is the main topic for this last part of chapter 24, and that is polarization.